Ensuring the safety and quality of packaged drinking water involves a multi-step process. Testing PDW is categorized into 4 areas, each focusing on different water quality aspects. Now let's explore 4 main categories of PDW testing. 1. Chemical testing. Chemical testing examines the composition of water to ensure safety. In chemical testing, 42 parameters are tested, which are description, 6 parameters in Table 1, 25 parameters in Table 2, and 10 parameters in Table 3. 2. Microbiological testing. Microbiological testing checks for harmful pathogens. 13 microbiological parameters are examined, ensuring the water is free from harmful microorganisms. 3. Pesticide residues. Pesticide residues can be harmful, so we test for traces of pesticides. 30 pesticide residues are tested to meet safety standards. 4. Radioactive residues, RAR testing. Radiation testing ensures the water is free from harmful radioactive residues by measuring 2 critical parameters, alpha and beta emitters. Now let's explore each test, starting with chemical testing. The first parameter, as specified under Clause 5.3 of IS 14543-2024, ensures the water is clear and free from sediments. For example, the bottle kept in the left is having visible impurities, which means non-compliance to the standard. However, a bottle kept in the right for illustration purposes is visually pure and free from suspended particles or extraneous matter and complying to our Indian standard. Color testing, based on IS 3025 Part 4, ensures water is visually clear. The maximum allowable color limit is 2 true color units, TCU. We use Nessler tubes and platinum cobalt standards to compare water samples to these color standards. Ensure the sample is filtered and free from turbidity to avoid interference. A compliant sample stays under 2 TCU. Anything higher may indicate impurities. Odor parameter testing, IS 3025 Part 5. Odor testing ensures the water is free from unpleasant smells. Basic steps include filling a wide-mouth bottle, insert the stopper, shake it vigorously for 2 to 3 seconds, and then quickly observe the odor. Report the true odor of the sample at the mouth of the bottle as rotten egg, burnt sugar, soapy, fishy septic, aromatic, chlorinaceous, alcoholic odor, or any other specific odor. In case it is not possible to specify the exact nature of odor, report as agreeable or disagreeable. Taste parameter testing, IS 3025 Part 8. Taste testing ensures water meets acceptable standards. Samples are prepared at 15 to 27 degrees Celsius and tested by a trained panel. The taste is rated on a scale from "I would be very happy to accept this water as my everyday drinking water" to "I cannot stand this water in my mouth and I could never drink it." Sample sheet is put at the right side of the video for more details. Testers rinse their mouths between samples to maintain accuracy. Turbidity testing, IS 3025 Part 10. Turbidity testing ensures water clarity. The maximum permissible turbidity is 2 NTU. Turbidity affects both the appearance and safety of drinking water. pH testing, IS 3025 Part 11. pH testing ensures water is neither too acidic nor too alkaline. The ideal pH for drinking water is between 6.0 and 8.5. pH outside this range can affect taste and safety. pH meter is first calibrated by known pH buffers of 4.00, 7.00 and 10.00, and then samples are tested. Let's explore the procedure for testing total dissolved solids, or TDS, in packaged drinking water using the gravimetric method. We start by preparing a clean, previously dried evaporating dish. We accurately weigh it and record the initial weight. A known volume of water sample, typically 100 milliliters, is transferred to the dish. The sample is first heated on a hot plate set at 98 degrees Celsius until most of the water evaporates. The dish is then transferred to a hot air oven, maintained at 180 degrees Celsius, to ensure complete drying of the residue. Once evaporation is complete, the dish is cooled in a desiccator to prevent moisture absorption and weighed again. The difference in weight represents the TDS content. First, we take 20 milliliters of the water sample and transfer it to a clean conical flask for titration. Next, we add a mixed indicator, which combines methyl red and bromocresol green. This will allow us to observe the color change during titration. We titrate the sample using standard sulfuric acid, which reacts with bicarbonates in the water, neutralizing them step by step. The end point is reached when the solution changes color from green to reddish-orange, indicating that all bicarbonates have been neutralized. Let's go through the procedure for testing chloride in packaged drinking water using the argentometric method. We begin by taking a 100 milliliter sample of the water and transferring it to a clean conical flask for titration. To the sample, we add a few drops of potassium chromate, which acts as the indicator in this titration. Now, we titrate the sample with standard silver nitrate solution. During the titration, silver ions react with chloride ions in the water. This reaction continues until all chloride ions in the sample have reacted with the silver nitrate. The end point is reached when the solution turns from yellow to reddish-brown, indicating that all chloride ions have been neutralized. For the remaining parameters, we'll categorize them based on the instruments used for testing. While many parameters can be tested with multiple instruments, we'll focus on one commonly used technique for each parameter. All instrument-based testing follows a known versus unknown approach. For example, first, we calibrate the spectrophotometer using known concentrations 5, 15, 25 and 35 ppm of CRM, certified reference material. Then we measure the unknown sample. By comparing its absorbance to the calibration curve, we determine the sample's concentration. Now we will move ahead to our first instrument. At the heart of our analysis lies a sophisticated machine known as the inductively coupled plasma optical emission spectrometry, or ICP-OES. This remarkable device allows us to simultaneously analyze 15 elements in a single operation, employing two distinct techniques: aqueous analysis and hydride generation. The process begins with the receipt of water samples from sample cell to our testing section. Our analysts meticulously prepare these samples, taking 10 milliliters from each and arranging them in specialized trays. The liquid sample is drawn into the peristaltic pump. In the nebulizer, it's converted into a fine aerosol spray. In the spray chamber, larger droplets drain away, but finer droplets are directed into the hot plasma. In the plasma, the sample aerosol vaporizes at 10,000 K, and its atoms and ions are excited so that characteristic wavelengths are emitted. The light is transferred into the high-resolution, no-purge sealed optical system, which separates the light into the specific wavelengths for the elements to be measured. As these wavelengths strike the detector array, light intensities for each different wavelength are quantified. Our sophisticated software converts them into concentration units. So the sample secrets, which elements it contains, in exactly what amounts, are revealed. The process is complex, but the results are very precise. Now we will move to another technique, namely UV visible spectrometry. Following 6 parameters are tested on UV visible spectrometry. 1. Nitrite, 2. Sulfide, 3. Phenolic compound, 4. Anionic surface active agents, surfactants, 5. Cyanide, 6. Sulfate. The UV visible spectrophotometer operates on the principle of measuring the absorption of ultraviolet UV and visible light by a sample. When light passes through a sample, certain wavelengths are absorbed based on the chemical composition of the substance. The spectrophotometer measures this absorbed light and generates a spectrum that shows the intensity of light absorbed at various wavelengths. In simple terms, the device shines light through the sample and records how much light is absorbed at each wavelength. The amount of absorption is directly related to the concentration of the substance in the sample, which follows the Beer-Lambert law. Nitrites are tested using a colorimetric method. The sample is treated with sulfonylic acid and NED solution to form a pink azo dye, and the absorbance is measured at 540 nanometers. Sulfides are tested using a methylene blue method. When sulfides react with N-dimethyl-P phenylnadiamine, they form a blue complex measured at 664 nanometers. Phenolic compound. For phenolic compounds, the sample reacts with 4-amino-antipyrine in an alkaline medium to form a yellow-orange complex. The absorbance is read at 510 nanometers. Anionic surface active agents, surfactants. Anionic surface active agents, like detergents, are tested using methylene blue. After forming a blue complex, the absorbance is measured at 652 nanometers. Cyanide. Cyanide testing involves a reaction with pyridine pyrazolone to produce a yellow-orange color. Absorbance is recorded at 620 nanometers. Sulfates are measured using a turbidimetric method. Barium chloride reacts with sulfate ions to form a white precipitate. Absorbance is measured at 420 nanometers. Nitrate and fluoride testing. Instrument, ISC meter. Nitrate and fluoride levels in water are tested using the ion selective electrode meter. This instrument measures the concentration of specific ions in a water sample. The calibration process is critical for accurate results. We use standard solutions to ensure precision before testing the sample. Once calibrated, the water sample is analyzed, and the meter displays the concentration of nitrate and fluoride. Mineral oil testing. Instrument, FTIR. The detection of mineral oil is performed using Fourier transformation infrared spectroscopy, or FTIR. This method involves analyzing the infrared absorption spectrum of the sample to detect hydrocarbons. The results help identify even trace amounts of mineral oil, ensuring water safety. Elevated levels of mineral oil may indicate contamination from industrial discharges or improper packaging materials. Bromate testing. Instrument, ion chromatograph. Testing for bromate is done using ion chromatography, a technique that separates ions and polar molecules based on their affinity to the ion exchange resin. Bromate is a byproduct of the ozonation process used in water treatment. High levels of bromate in water can be carcinogenic and are strictly monitored. Uranium testing. Instrument ICP-MS. The testing of uranium is conducted using inductively coupled plasma mass spectrometry, or ICP-MS. This advanced instrument detects trace levels of uranium with high precision by ionizing the sample and analyzing the mass-to-charge ratio of the ions. Packaged drinking water may contain harmful contaminants such as pesticide residues, PCBs, and PAHs. These substances can enter water through agricultural runoff, industrial discharges, or environmental pollution. Their presence, even in trace amounts, can have serious health impacts. Let's now look at how pesticide residues, polychlorinated biphenyls, PCBs, and polycyclic aromatic hydrocarbons, PAHs, are tested. Before analysis, contaminants are extracted from water using liquid-liquid extraction or solid-phase extraction. These techniques are commonly used for pesticides, PCBs, and PAHs. Their purpose is to concentrate the contaminants for precise analysis. GCMS-MS, LCMS-MS. GCMS-MS is used to analyze volatile and thermally stable compounds, including pesticides, PCBs, and PAHs. These contaminants often share similar extraction mechanisms, enabling streamlined testing. The instrument ensures high accuracy, even for trace-level detection. Non-volatile and thermally unstable pesticides, such as 2,4-D and isoproteron, are analyzed using LCMS-MS. This method is ideal for compounds that degrade at high temperatures. Microbiology. 1. Membrane filtration for pathogens. The membrane filtration technique is used to detect microorganisms like E. coli, coliform, fecal streptococci, Staphylococcus aureus, Pseudomonas aeruginosa, yeast and mold, Salmonella, Shigella, Vibrio cholera, and Vibrio parahemolyticus. Here's how it works. A 250 milliliter of water sample is filtered through a membrane with 0.45 micrometer pore size, which is small enough to trap bacteria. The membrane is then transferred to a selective culture medium and incubated under conditions specific to each microorganism. After incubation, some bacteria need further enrichment in the medium, while other bacterial colonies are identified based on their initial appearance, such as color and morphology. After the initial detection of bacteria colonies, further confirmation is done through biochemical tests. These tests validate the presence of specific pathogens by analyzing their metabolic activity. 2. Aerobic microbial count, AMC, at 20 to 22 degrees Celsius and 37 degrees Celsius. Pour plate method. To test for aerobic microbial count, AMC, the pour plate method is used. This method quantifies the total microbial load in water under two temperature conditions, 20 to 22 degrees Celsius and 37 degrees Celsius, simulating different environmental and body temperature scenarios. Here's how it works. 1 milliliter of water sample is taken into sterile Petri dishes and pour plate with molten agar medium and mixed. After solidification, the plates are incubated at their respective temperatures for 24 to 72 hours. Bacterial colonies that form are counted and reported as colony-forming units, CFU. 3. Sulfite-reducing anaerobes, heat-treated water sample in DRCM. The test for sulfite-reducing anaerobes involves using a specialized medium, differential reinforced clostridial medium, DRCM. This test detects anaerobic bacteria that reduce sulfite and may indicate fecal contamination. Here's how it works. A 50 milliliter water sample is heat treated to eliminate non-spore forming bacteria. The treated sample is then added to 50 milliliters of double-strength DRCM. 2 milliliters mixed solution of ferric citrate and sodium sulfite in equal amount to be added in the inoculated sample. Addition of red-hot iron wire with the layer of paraffin liquid may aid anaerobiosis. Inoculated sample is then incubated at 37 degrees Celsius for 48 hours. Growth is indicated by black precipitates, confirming the presence of sulfite-reducing anaerobes.